אפשר. אהלן, ערב טוב. טוב, אז התכנסנו כאן למפגש מיטאפ נוסף של קהילת ביג תינגס. יתחיל את ההרצאה שלו עכשיו אבישי איש-שלום מפewbytes. הוא ידבר איתנו בגדול על גריד קומפיוטינג ועל Yarn versus Mesos. שני, אפשר להגיד, קלאסטר מנג'רים, וניתן את הבמה. תודה רבה שהגעתם.
טוב, לא יודע אם צריך פה דבר אחר.
נראה שכן.
ביקשו ממני לדבר באנגלית, אז יש פה מישהו שיש לו בעיה עם זה, או שכולם זורמים עם אנגלית? מישהו, משהו? Okay, so it's English then. So hi, my name is Avishai, like you said, and I'm from a company called fewbytes. It's a consulting company. We do a lot of infrastructure work and a lot of other stuff. You don't really care about this, so I'm going to skip it. This talk is about grids in general, Yarn and Mesos in particular. And this is the first talk of a series of two talks. The next talk is going to be in August. And this talk is more high level. It's more about architecture and about use cases and what is a grid and that kind of stuff. And the next talk is going to be more low level. It's going to be on APIs and how that stuff actually works, containment, all those cool things. So if you care about the low level stuff, make sure that you register to the one in August. And if you don't, then just don't. So that's about it. So I'm going to start with a quick question. Who works with grids here? Show of hands. Not a lot of people. So who works with Yarn? Okay, who works with Mesos? Oh, 2 people. That's nice. In production? 0 hands. Okay, nice. So as you gathered, Yarn is much more popular than Mesos. I'm not exactly sure that's for the right reasons, but we're going to touch on that a bit later. So what's a grid? Originally grids, and I'm going to talk about that in a bit, originated from HPC, high performance computing. It's like supercomputers. And basically it's a collection of computer nodes doing a shared workload. Okay? Shared workload could be some kind of distributed computation, could be something like a web service, distributed database, and so on. And it's usually general purpose. Like you have clusters that do one job and only one job. And most of the grids, in general, they serve a general purpose. They're more general purpose. They host a variety of jobs. And usually they don't belong to a single team, so a lot of teams use grids because they are very expensive and you want to use their capacity and their time as much as possible. So in universities, back in the days, you had several clusters that were connected to a universal grid. And the grid managed several clusters, and you could submit your job to a grid, and the job would run somewhere on some cluster, somewhere. You didn't really care where, you didn't really care how. You only cared that it ran on the computers that that could run it. Depends on architecture and that kind of stuff, and that you got then the result after 2 days when your computation is completed. So that's the general idea. So let's talk about the history of grids. Before we had grids, we had large supercomputers like mainframes. We all heard about Cray computers. They were very, very expensive. They cost a lot of money, and they performed amazing work. They were very, very fast. They had a lot of bandwidth and a lot of power to them. But we needed something that was cheaper. We needed something that could do a lot of job, a lot of work, and still cost reasonable amounts of money. So we wanted to use the hardware we had, which was at the time something like this, desktops, basically, or like office servers. And that was the start of something that was called Beowulf clusters. Beowulf clusters were kind of makeshift. People just gathered around all the boxes they had, connected them, and ran some kind of grid software on them. And the grid software kind of transformed those resources into a pseudo supercomputer. Now this pseudo supercomputer didn't run normal jobs. You had to program your software in a very, very specific and different way to make it work. You couldn't just run distributed software on it. Like in Cray computers, you had shared memory. Between those nodes, you didn't have any shared memory. So you needed a completely different programming model. Most of the people that use Beowulf clusters were in universities. You could actually see some of them in the industry, mostly pharmaceutical companies, places that needed to do scientific workloads. So the usage was kind of similar, and it was mostly restricted to universities. BOINC is a very different beast. I don't know if you've heard about it. Have you heard of the SETI at Home project? Yeah, anybody?
Yes.
Yeah. So that was a very cool idea. The idea was to use the work power and the untapped resources of your desktop at home. So basically, they split the job to a lot of small pieces, and you would run BOINC, which was like the grid endpoint on your laptop or your desktop. And whenever you weren't using the laptop or desktop, like when you had the screensaver on, then BOINC would start running that job on your computer, parts of that job. And it would take data from the internet, process it, and submit the results back to the grid. And that was like a highly distributed grid that was kind of loosely connected. And it was awesome because it used a lot of resources that people just left idle most of the time. So that was a very special grid. And I think that was very innovative for the time. So the basic architecture of a grid is something like this. You have a scheduler, and the scheduler has a job queue. And the user submits a job to the queue, where the job waits for available resources. And the job of the resource scheduler, the resource manager, is to know where in the cluster we have available capacity. And if we have available capacity, it submits a job to that node, to the node where capacity is available, and runs the job there. So suppose I have a job and I need like 100 CPUs for that job, and I ask the job scheduler, can you schedule that job to be executed on a cluster that has 200 CPUs? So the scheduler would wait, my job would wait in the queue until 100 CPUs become available, and then it would submit parts of that job to different nodes. So for example, suppose every node had only 8 CPUs, so it would submit my jobs to like 20 or 30 different nodes, and then when I have enough capacity, my job would stop running. And it would run until it's completed, it could take a few days, and then capacity becomes available again. And of course, I have to submit my binaries somehow, because my program is always composed of data and executable code, and the resource manager only provides a mechanism to submit the commands of running those in the job, doesn't actually distribute the executables and the data. So I also need a global file system. So in traditional HPC grids, you would always have a global file system, something like an NFS or a NetApp or AMC or something like that. And all the nodes would have access to that storage where all of your data and all of your executable codes would reside. So that's a general idea. And assignment of jobs was based on load, sort of. It was pretty primitive actually. And on attributes. What do I mean by attributes? For example, architecture. If I have a job that was compiled on 64 bits computer, then I need only nodes that are 64-bit capable. So I have some limitations. So the responsibilities of grid are basically to schedule the tasks and distribute them, to load balance the load between nodes. So I won't have nodes that don't do anything while other nodes are overloaded, so on. Monitor the resources. If a node falls down, if a node shuts down or has a problem, if a node is overloaded, then don't submit more jobs to it, that kind of stuff. Retry failed tasks. If a job has failed, you need to try it again. And of course, do all other stuff like system administration tasks, like collect the standard out and standard error of your jobs, because it's unreasonable to ask the user to go and log into every node in the cluster just to see the logs. Think that if you have 200 nodes and your job ran on 40 nodes, you don't even know which nodes, how are you going to get the logs? So the grid has to somehow get all the logs for you and sometimes aggregate them. And of course, job history. What do I mean by job history? If I'm a user of a cluster and I've submitted like 10 jobs, I want to be able to do something like job list and get a history of all the jobs that I ran, when did I run them, are they finished, are they still running, that kind of stuff. So it has to maintain kind of a database of jobs. So the HPC grids of all times, those were the original grids, were built mostly for offline batch jobs. And what do I mean by offline batch jobs? The jobs were pretty long. They took from hours to days, and they weren't user interactive. I mean, I would submit a job, and I would get a mail like 2 days later, your job is completed. It's not like I would be sitting next to my terminal and see the job running. There was no progress bar or anything like that. There was no API. The way I worked with the grid was using CLI tools. I couldn't program the grid. And it was pretty simple, and the task placement logic was mostly based on simple heuristics like can that node run my executable or not, and how much noise does it have? Nothing more than that. And it was not preemptive. Not preemptive means that if a job already ran on that node and the resources were used, there was no way to free the resources on that node. Preemption means that I somehow remove the job from that node. Think about your operating system. When you have more than one process on your CPU, the operating system suspends temporarily the process that is running and allows the other process to run on your CPU. And that grid was not capable of doing that kind of stuff. So if I somehow hogged the resources, I ran a job that took all the resources of the cluster, nobody else could use that cluster until my job is completed. That sucked. Resource assignment was kind of bulky. What do I mean by bulky? If I ran a job in the cluster, I could ask for CPUs. And what happens if I got one CPU and I was using only 50% of that CPU? Wasted resources. Okay, so the granularity of resource allocation was pretty bad. We had to assign strict slots, like we defined a slot to be one CPU and 2 gigabytes of RAM, and this was the granularity of the entire cluster. We couldn't do anything better than that. So there were a lot of wasted resources. And of course, no code distribution mechanism, that's what we needed global file system for, and no isolation and containment. Processes on the grid ran as normal Linux processes, which means that they could interfere with each other. They could hog resources of one another. They could fill up the disk. They could do a lot of nasty stuff. We didn't have containers at the time. So that's how HPC grids ran. And surprisingly enough, it was actually pretty good. You would expect, being this so simple and so fragile, that would be pretty unusable, but it wasn't. It was pretty good, actually. But then again, the users of those clusters all worked at the same place, and we could discipline them. As a cluster administrator, you could go to your user and say, your program is doing something nasty, I'm going to shut it down. I'm going to kill your job. And then he would go and fix his code. And this is a privilege that not all of the administrators have. So, something to think about. But usage of HPC grids were mostly limited to universities. And you didn't see a lot of it on web companies and that kind of those kind of places, until, anybody can take a guess, was the first company that implemented wide-scale grid for general purpose computing? Of course, Google. They invented something called Borg. Yeah?
In 2003?
Actually, I'm not sure exactly when it went into production. I think it was 2003, maybe 2004.
We implemented in 2002.
What did you implement in 2002?
We did massively scalable image processing on 800 blades on each side.
How many applications?
Multiple applications and semiconductors.
Okay. Was it user-facing, interactive jobs, that kind of stuff?
Operator-facing, not user-facing.
Okay. So that's pretty impressive, but there's a big difference, yeah. So yeah, there were other grids before, but Borg was the first grid that I know of anyway, that ran web servers and user-facing servers and that kind of stuff that required low latency. Batch jobs and jobs that only face the operator can have very large latency. For example, if I'm an operator and I have to wait 2 seconds to get a response to my input, then it's not so bad. Nobody gets upset. Batch jobs, latency could be hours. But Google runs stuff that we're user facing. Like if you go into Gmail, you get a response in 50 milliseconds, and you get annoyed if you have to wait. So it's pretty risky to run it on something that shares resources. So it was really impressive. They started using it in production around 2003, 2004, not sure exactly when. It was a secret for a very, very long time. There were rumors, people spoke about it here and there, people that left Google spoke about it, but it was mostly secret until they published an article last year. And now we know not everything, but a lot. And it was pretty impressive. It ran both offline batch and batch tasks and online applications. It ran the database, big table, and a lot of other stuff. It had very granular resource control. You can schedule on Google Borg, you can schedule as much as 0.01 CPUs. So it has very granular resource control. It's very dense, which means that the resource utilization of Borg is very, very high. That was the whole idea, the whole point behind Google Borg, to utilize the data center as much as possible. And it has very sophisticated and application-aware API, which means that Borg can schedule tasks according to application logic. For example, if I have an application that requires redundancy, I can say something like, my tasks need to be on different machines because I don't want one machine to take out more than one instance of my application. And a lot of other stuff, like they have something called affinity, anti-affinity, and even data center aware and rack aware and a lot of other cool stuff. So it's, so.
It was in a single data center or in multiple data centers?
Yeah, so Borg itself is contained to cells, in cells that, I think the biggest cell is about 20,000 machines.
Oh.
So it doesn't exactly scale data center, but the way the data center is built is they have crates, and every crate has its own power supply and its own
but it was
cooling.
in the United States probably, right?
I think now it's running in all of the data centers as far as I know. So it's crate aware. We don't really have that term in normal data centers, so yeah.
Was it already using containers, Linux containers, back then in 2003?
So
Can you repeat the question?
Yeah. So the question was, how was container technology back in 2003? And the answer is pretty crappy. They improved it along the way. It started out with only truth and a few other stuff like different user and R limit. And along the way, they added a lot of kernel patches, which today compose what we call Docker and LXC. Most of the kernel code for that was contributed by Google, obviously. So that's why. It was also preemptive, which was pretty innovative for grids. And that was very, very cool, because what they did was that when they had increased demand on the user-facing services, for example, during peak hours of Gmail or YouTube, the grid could turn off batch jobs like machine learning and data processing to make room for more traffic, which was awesome. So they didn't need to install more servers to serve more capacity. They could just shift the load between different types of jobs. So that was awesome. What about everybody else? They all tried to do something similar. So Facebook has something called Tupperware, which is also a grid that is based on Linux containers. There's not a lot of information about it. There is one talk in YouTube, you can look it up. They describe the rough architecture of Tupperware. Twitter uses Mesos, Yahoo uses Yarn. There are other users of Mesos and Yarn, but those are the notable users. So I'm going to talk a little bit about the history of both in a bit, so I'm not going to spend any more time about this right now. Yeah.
Is Google Omega related to Borg in some sense?
Yes, it
Can you
is.
repeat the
It
question?
is Google Omega related to Borg? So Google Omega is related to Borg. It's based on a lot of learning that they have from Borg. In the Borg article, they describe that Omega is actually a new scheduler for Borg, and it's very similar to the architecture of Mesos in the sense that it has different external schedulers, but it's not exactly clear how it's working because they haven't published the details. So, yeah, that's about it. So, building a grid is pretty hard actually. You have to deal with a lot of things that are counterintuitive and we don't think about all of them. If you have to work in very large clusters, then some of the stuff may be obvious to you, some of it might not be obvious to you, so I'm going to talk about this. For example, you have to handle stuff like input and output. You have to somehow get the binaries and data to all of your cluster nodes. You have to sometimes do copy to local. It's called localization in Yarn speak. Copy from remote file system or remote storage some artifacts to the local node, either for caching or to allow it to run. For example, a lot of the software that we have use something called memory map. And memory map only works on local, on local resources, or if you use some kind of kernel file system. So you have to do that. You also have to deal with logs. Not all of our programs log to standard out. So sometimes you have to copy files. You have to tell the grid, those are my log files, and you have to copy them to some central location, and you have to do this periodically, because otherwise I could only see the logs when the job ends. That's very bad for interactive jobs. So nowadays we have a lot of stuff like Logstash, which streams log to a central location, but grids usually provide this as a service. You also have to think about how to distribute your workload. Some of our programs know how to deal with, to be elastic. For example, if you have a stateless application, web applications in general, it's pretty easy to scale them up and down. Just add nodes or remove nodes. And the load balancer, kind of deals with it. If you have a new node, you just register it in the load balancer. The load balancer would shift more traffic to it, and everything, kind of smooths out in a few minutes, or even less. But not everything is like that. So, for example, if you have stateless web applications, it's pretty easy. MapReduce is another example because every task is pretty short. It could take like 10 seconds or half a minute, and then you can just spread the load to new nodes whenever a new task starts. Of course, it's also easy to resume dead tasks. Just boot up another task. Doesn't cost a lot. The cost is the cost of computation of one task. In a web server, it's maybe 100 milliseconds. In a MapReduce, it's a few seconds, but nothing more than that. But other workloads are very rigid. You can't change the number of tasks. You have to decide on the number of tasks in advance. And after the job is started, you can't change that in any way. Task termination, if only one task is terminated, the entire job is halted or cancelled. Depends on the particular job. And of course, this happens a lot when you have partition data or partition state. So the common example is MPI, where you separate the computation to different parts, and every part is done in parallel, but you need all the parts to complete for the entire job to complete. So if one part of an MPI job fails, you're screwed. You have to start from the latest snapshot. So that means that you could end up losing the entire computation or a few hours of computation if only one task is errored out or killed or whatever. Another example is something like Solar or distributed database. If you lose one shard of Solar, then you have a problem. You can't use it anymore. You lose one part of your index and you're screwed. And you can't reshard, you can't rebalance without it costing a lot of time, a lot of computation. So anybody working with distributed databases is aware of that problem, and yeah. Yeah, so you have replication, but if both of if you have like 3 replicas and all 3 of them are down, you're screwed. But also remember that you can't, for example, scale up, because even if you can add replicas, that doesn't help write throughput. It only helps read throughput. So if you want to scale writes, for example, you need to reshard the cluster.
Right.
So
there are databases that do that.
Like Cassandra.
Yeah, so Cassandra uses a different trick. Up until version 1, they had the same problem, and then they switched to something called vnodes. And so instead of sharding to the number of nodes, they shard to 256 times the number of nodes you have. So they just shard it to smaller parts, and then they shift those parts around.
Yeah, and
So
they can rebalance the cluster if
they rebalance by moving vnodes around. Yeah.
vnodes and consistent hashing also have a problem that you need to decide in advance how many vnodes you have.
Exactly. Same problem, but they just do it in finite
Smaller batches,
yeah, in smaller batches. So a lot of other databases have this problem, and API jobs, and a lot of other stuff. And it's a problem for grids, because if you have a rigid job, then it's going to take up the same amount of capacity that you started with. If you have more space available, more capacity available, you can't use it. If you need that space because you have higher priority jobs, you can't use it, because if you preempt even one task, you preempt the entire job. So that kind of kills a lot of the grids. Then you have a problem with task lifespan. Short tasks are very easy to balance, because when they end, you just schedule another task somewhere else. Or you can kill the task. It doesn't cost you a lot of money or a lot of resources to retry it, because it's a short task. You can do preemption. That opens up the new features and new ways to balance a cluster. But there is a problem with very short tasks. Ideally, for load balancing, we would want all our tasks to be as short as possible. But the problem is that starting a task could take some time. With MapReduce, for example, it could take a few seconds. And if your task is going to take 10 seconds, and it's going to take you 5 seconds to start that task, that's not very economical. It's going to slow you down considerably. So there's a trade-off between our ability to balance and our ability, the minimal amount of time that is still reasonable for a task. So I don't know if you like what you've heard so far. Grids are very hypey right now. Everybody wants a grid, and Docker is creating a grid, so now everybody wants Docker and a grid. It's very hypey, it's very trendy, everybody wants one. And if you're not hyped just yet, then you should be, I hope. Grids provide a lot of benefit, even if you don't care about all that other stuff. You get a lot of automation out of the box. You don't have to deal with servers, you don't have to install servers, you don't have to deploy applications on your servers. You don't need to do all that pesky process management, like using daemon tools and init scripts, and all that annoying stuff. Node supervision, process supervision, you get all this for free. And that's really cool, saves a lot of time. It also helps with density. So I don't know if you guys read Gartner or all those IT journals, but can anybody tell me what they think is the normal utilization of a data center?
7 to 30%.
7 to 30%, yeah, that's
13.
correct. To 13%, yeah, something like that. So the number I know is less than 20%, so that sounds about right. But yeah, that's the general status that we have in most data centers. So just think about this number. Less than 20%. And it's not surprising. I'm pretty sure if you go to the computers in your company and you do top on random machines, you're going to find that most of your computers are not doing anything. You're wasting a ton of money. You're wasting the cost of servers, you're wasting power resources, you're wasting cooling resources, the man hours that are put into production to keep those servers running for 20%, less than 20%. So it's pretty annoying. How can we drive utilization up? Yeah, so?
But just to be more accurate, it's the average, right? There are times where it's
Yeah, of course.
80%.
Yeah, which is part of the problem, because if your workload has peaks, you have to plan for the peak. So you have to have a lot of hardware for maybe 5 minutes a day, an hour a day. It's pretty annoying. So how can we drive utilization up? Of course, by sharing complementary workload. What do I mean by complementary workload? For example, some loads require CPU, some workloads require RAM, some workloads require disk. And if I could use the same servers to store data and to do those CPU intensive jobs and to cache stuff in my RAM, then I wouldn't need a separate Memcache cluster and a separate HDFS cluster and a separate machine learning cluster, for example. And that would save me a lot of money, because that means I can use maybe a third of the amount of machines. So we want to drive utilization up. How do we do that? By sharing workload, and grids helps with sharing workloads. We need priorities for that, because some jobs are more important than other jobs. And of course, grids know how to do that as well. But most importantly, it provides abstraction, which means that I, as a sysadmin or as a programmer, don't give a fuck about IP addresses, servers, disk, or racks. Just annoying stuff that I have to deal with because nobody has solved that problem for me. Why do you care what machine your job is running on, or your server is running on? Like, seriously, what do you care? Like, I see people every day logging into servers and they're like memorizing the IP address of that server and the location and the disk where the data is saved and a lot of other stuff that for me are meaningless. It's like, what the fuck do you care about that? So I don't. If I have grids that do that for me, I really don't care. And that's awesome. So if you don't want a grid just for doing all that other stuff, then abstraction is probably the reason why you do want it. And of course, we don't all have grids, because grids is not so easy yet. It's going to be a lot easier. But when we finally do have grids, then we're going to have all of that. Here's a side note. You're all already using a grid. Anybody want to take a guess which grid it is?
Power grid.
Sorry?
Power grid.
Power what?
Power grid.
Power grid? No.
Google.
No. Which one?
Google, Amazon.
Amazon, yeah. Yeah. Anybody here not using Google Computer Engine or Amazon or OpenStack or Azure or one of them? Okay, I don't really, of course. So if you're using one of those, then you're using a grid. That grid happens to be running virtual machines instead of containers, but it's still a grid. It provides all those abstractions that I've talked about. It shares workload, it handles priorities, and in some cases, it can even preempt your machines. Think about spot instances or preemptive instances in Google. You might not be surprised at this point to learn that Google Computer Engine is actually KVM running on top of Borg. So, yeah. So we are all already using grids. We just don't have private grids. We're using public grids. And our containers are a little quirky. They're not Linux containers, they're virtual machines, but it's generally the same idea. So, let's talk about Yarn. Yarn is an acronym for yet another resource something. Not even sure again. Sorry? Negotiator, yeah, thank you. It's basically a big ball of yarn. And this grid is the resident grid of hadoop. For anybody who doesn't know what hadoop is, and anybody doesn't know what hadoop is? Seriously?
I don't know what Hadoop is.
Okay.
Some kind of buzzword.
He doesn't recognize the phrase.
Okay, so I'm going to explain what Hadoop is. So Hadoop is a data processing platform that is comprised of multiple services. One of the services is HDFS, Hadoop File System, which is basically a distributed file system built for very large objects, for very large files. Another very known component is MapReduce, which is a framework for doing distributed data-intensive calculations. And there are a lot of other parts. And one of the parts in the recent versions of Hadoop, anyway, is Yarn, which is the grid component. So Hadoop is like a very big word to say something like a framework of a lot of services and a lot of frameworks. It's like an umbrella project, if you want. Wow. Anyway, so Yarn, yeah. What was the motivation for Yarn? So MapReduce, the original MapReduce version, MR1, as they call it now, didn't scale very well. It had only one job tracker. The basic architecture of MapReduce was that you sent your job to a job tracker, and the job tracker would split it to a lot of small tasks, mappers and reducers and that kind of stuff. and it would allocate them to something called a task tracker. You would have one task tracker daemon on every node, and to send the task to those task trackers. And the problem was that you had only one job tracker that handled all the jobs of all the users on all the cluster. So it didn't scale very well, as you can imagine. It had to track tens of thousands of tasks per job, and you had multiple jobs per user, and you had multiple users. So that was a problem. Other than that, they had a problem with resource utilization, because a MapReduce cluster would have special slots for mappers and special slots for reducers. So if you used all the resources, all the slots of mappers, but you didn't have any reducers, you would waste like a third of your cluster capacity, which was, again, annoying. Other than that, you had a problem with multi-tenancy. Everybody was using the same job tracker, and if you had two teams using the same job tracker, they could essentially take each other's capacity and fight over it at lunch and spill coffee at each other. Not bad for business. Sorry, not good for business. Depends what your business is, I guess. Another motivation was that they wanted to run something else, not only MapReduce. More and more frameworks were appearing for data processing other than MapReduce. Things like Impala, Spark, like cool stuff, and they wanted to be able to use the cluster without having to rewrite the job scheduling component over and over again. So eventually they wanted to write Yarn, but they didn't. Instead they wrote something called Hadoop on demand. Didn't work as well as they thought. So when it failed, they wrote Yarn. And it didn't exactly fail, but didn't work as planned. They started development around 2011 in Yahoo mostly, and a little bit of help from Facebook. And it was released to the general public in Hadoop 2.2, which was actually pretty late. I think it was the end of 2013, or more or less. Not very long ago. And this is the general architecture of Yarn. So the idea is this. You have a resource manager, surprise, and you submit jobs to the resource manager. Again, big surprise. But here things get a little interesting. You have something called an application master. So the first task that is initialized when you submit a job is a special task called application master. And this task basically does the orchestration of the job. It holds application-specific logic of how to handle the tasks on your cluster, and it talks to the resource manager and basically says something to the resource manager. I need 3 containers of that type, and I want them on those nodes. And I want 100 containers of that type, and I don't care on what node you put them. And that allows us to do a lot of cool stuff, because the application master can, for example, have retry logic. If a task fails, it gets notification, gets a callback, and it can start another container to replace it. It can choose not to start another container to replace it, whatever it wants. So, yeah.
But the containers are Linux containers or like different kind of JVM containers?
So the question is, are the containers JVM containers or Linux containers? And the answer is it can be either Linux container or a Windows process. It's not a JVM container in any way. The JVM is only used for the agent to start processes. It's not limited to Linux containers. You can run Yarn on Windows nodes. I don't know anybody who does that, but you can. But yeah, anyway. So the application master holds the application-specific logic, and it talks to the node managers to get status of containers, and to the resource manager to get the status of the job, and tell it and to give it commands like run more containers and destroy containers and that kind of stuff. So that's where the architecture really deviates from the old-time grids. Okay? But everything else is pretty much the same. Yeah. So let's do a quick summary of the architecture. Yarn has a monolithic scheduler, which means all the scheduling logic is in the resource manager. It has different types of schedulers. You can change scheduling algorithms. it's pretty sophisticated, but still, it's all in a central location, and all scheduling done there. You have application-specific callbacks to customize application behavior using the application master, and you have one executor on every node, okay? And it's pluggable. What I mean by pluggable, you can replace it. It can be either a Windows executor or it can be a Linux executor. And we actually have two types of Linux executors, one using C groups and one using Docker. Okay? The Docker one is pretty crappy, but yeah, that's not the point. So let's talk about Mesos. Mesos is a very cool grid. That was originally a research project in Berkeley, and at some point the guy from the Berkeley thingy went to Twitter and he gave them a talk about Mesos, and in the crowd were engineers that used to work for Google and really missed Borg, and they were like, oh my god, I want this. So Twitter became early adopter of Mesos. And it's running in production in Twitter and Airbnb since around 2010, which is pretty awesome. And they improved Mesos tremendously. They also got a lot of input from the Google Borg guys, because Silicon Valley is such a small place, obviously. So a lot of the input went into the design of Mesos. It became an Apache project around 2013, and it's only getting more momentum since. Pretty awesome. So this is the general architecture of Mesos. And Mesos is very, very different from all the grids that we know and love. First of all, the scheduling logic is split in two. So you have the Mesos master, who is in charge on tracking the resources in the cluster, what's available, but it doesn't actually schedule jobs on nodes. Okay? What it does instead is offer resources to the second part of the scheduler, which is called a framework. And you have different frameworks, and the Mesos master would say to the framework, listen, I have free capacity of about 100 CPUs and about a terabyte of RAM, and it's available on those nodes, and do you want this? And then the framework would look at those available resources and say something, you know what, I want this slot here and this slot here, and a container here and a container here, and yeah, run this for me, please. And the master will do that. And that sounds pretty dumb, right? But there is a lot of power to it, because the responsibility of the master is to balance the capacity, or should I say, the fraction of the cluster that is available to every framework. And every framework gets like its own dynamic subcluster where it can schedule its own resources according to its own application-specific logic. So think about very different types of workloads like MPI scheduler. And as you remember, MPI can only use static resources. It can only decide upfront how many tasks it will run. It has very long-running tasks, so it behaves in a very, very different way than Hadoop jobs. Hadoop jobs have very short tasks, but they care about data locality. So a Hadoop job, for example, would probably prefer waiting and not start a task on nodes where data is not available, and start them at the next round where nodes that have data locality become available. So it's very different behavior. And this split allows basically Mesos to satisfy the demands of everyone. Yeah. Any questions? No? Okay, great.
Is that a distributed file system, or is it completely independent of storage?
Yeah, so both grids. Yeah, the question is, does Mesos have a distributed file system, or is it independent from storage? So both Yarn and Mesos are actually independent of the global file system. Yarn does have some integration with HDFS in the sense that it uses HDFS to distribute files. Mesos doesn't have that kind of mechanism, but in general, both can work with different file systems. So another thing that is very, very different in Mesos than Yarn and traditional grids, that Mesos actually has multiple executors on slave nodes, on worker nodes. every framework can potentially have its own executor, which is again very powerful because they can launch tasks in very, very different ways. For example, API executor can use C groups and Hadoop can use Docker. Or they can start Java processes, the Hadoop executor can start Java processes, not use C groups, whatever they want. It's up to them. They get their own logic on the node. And this is the high-level architecture of how it's built. Basically, you have Mesos master and the Mesos secondary, the standby node. And it talks to the framework using RPC directly. And everything is coordinating using a zookeeper cluster. Okay, that's very important. Yarn doesn't have this. They intend to introduce a failover mechanism at some point, I think like in 2.7. Right now they don't have it. And everything is coordinated using the zookeeper cluster. Okay? So, a summary of the architecture. The schedule is split in two. It's two-stage scheduler. Frameworks take care of the application-specific part. They get resource offers from the Mesos master, and you have multiple executors on every node. So let's talk about which is better. Yeah. Anybody have an opinion yet?
Probably Mesos.
Scorpion, yeah.
It depends.
Depends, yeah. So let's talk about workload. Yarn was mostly built for data processing workload. And it really shows in the design and also shows in the behavior of Yarn. In contrast, Mesos was designed for generic workloads. This is why you have frameworks. Mesos supports Docker pretty much out of the box. Yarn has pretty crappy and quirky Docker support. What do you mean by that? It means that it can run Docker, but the Docker containers have to contain the Yarn jars inside, which is like, what the fuck? It means that you can't use images from Docker Hub, not vanilla images in a way. Mesos supports a lot of cool stuff out of the box, like Spark and Storm. Spark was actually written for Mesos originally. Yarn doesn't really have a lot of generic applications that support it, but it does have a lot of data processing applications that support it. In fact, there are more data processing frameworks that support Yarn than there are that support Mesos. And that's not surprising because a lot of those frameworks are part of the Hadoop project. So there's that. On the other hand, Mesos has a lot of other stuff that supports it. Like if you want to run something like a web server, then probably Mesos would have better support. You have a lot of generic frameworks for Mesos. Notable frameworks are Marathon and Aurora, or if you've heard of them. They basically allow you to run a generic Docker container on Mesos Grid very, very easily using a very simple UI or REST API.
Myron.
Yeah, sorry?
Myron, that runs Yarn over Mesos.
Yeah, I'm going to mention it in a minute. So, yeah, for that, yeah, sorry?
But then when you run Marathon, is it like another framework in Mesos?
Yeah, Marathon is a Mesos framework.
And everything that runs behind Marathon is not directly speaking with Mesos scheduler?
No, no.
So it's a problem, right?
No, it's not a problem.
You lost the quality of the scheduler. Because you now speak with the scheduler of Marathon and not with the advantage of
Yeah, so that's something that's very important to mention. You always, as a client of Mesos, you always speak to the framework. You almost never talk to Mesos itself. You always work through a framework. So it's the same with Marathon. You talk to Marathon, you ask Marathon to run your Docker container on the grid. Marathon talks to Mesos, and that's how it happens. Yeah.
Do I understand correctly that Mesos Master is like a marketplace, like a stock exchange, where compute node gives offers, or executor the compute node gives offers, and frameworks take bits for the
More or less. So the way it works is that the Mesos Master tracks the capacity of all the nodes, and it aggregates all the capacity in a resource offer. It has like a view of all the capacity that is available in cluster. It takes some part of available capacity and offers that to a framework. And the reason it only offers only a part of the capacity is to maintain quality of service for different frameworks. Okay? and it's dynamically adjusted, so eventually if no other framework uses that capacity, then over time, the framework that does use the capacity will get all the available capacity. But it tries to maintain quality of service between frameworks. Okay? So we're moving on. Yarn can run generic applications. Okay? There are a couple of application masters that allow it. Notable projects are Apache Slider, for example, that allows you to run generic applications on Yarn. And by the way, Storm on Yarn uses Slider, and you can too if you want. You can write your own application master. Believe me, it's not fun. The API is just horrible, but it can be done. You can use other frameworks like Slider. There are other frameworks like something called Kitten, and probably other frameworks that I'm not even aware of. And going back to Mesos, writing a Mesos framework is actually pretty easy, but I don't see any reason why you should do that. There are plenty of frameworks. You probably will find something that you like. Unfortunately, not all applications have frameworks, and you will probably have to write some code to make everything run on Mesos. That's a bummer. Let's talk about ecosystem. So Yarn is kind of a Hadoop sidekick. It's not. I don't know of anybody who's using Yarn just for Yarn. Everybody I know that uses Yarn because it's part of Hadoop, and they have Hadoop. That's why they have Yarn. That also means that you don't have any company that supports only Yarn and concentrates on developing Yarn and adding features to Yarn. The main backers of Yarn are the main backers of Hadoop, Hortonworks, Cloudera, those sorts of companies, and they're interested in a lot of things that are not Yarn. Also, the documentation is like, and yeah, some of it is good, some of it is not so good, and of course, Slider, which helps a lot. Mesos, on the other hand, has awesome support from Mesosphere, which is a company that is dedicated to making, to selling support for Mesos and developing ecosystem around Mesos and making it an enterprise-ready product. They have something called DCOS, okay, Data Center Operating System, which is pretty awesome if you can afford it, and has very good documentation. Has a lot of cool frameworks that make your life very easy, like Aurora, Marathon, and Kronos, which is like distributed cron. And of course, there is something called Project Myriad. Project Myriad allows you to run Yarn on Mesos. Yes, it can be done. It's like alpha quality right now, but it exists. You should know that also there are projects that allow you to run Kubernetes on Mesos and Kubernetes on Yarn. Again, alpha quality at best, but it does exist. So it's possible, at least in strict sense. So how is it extending Yarn and Mesos? I can tell you that extending Yarn is not fun. The API is not very well documented. It uses protobuf and some kind of custom RPC protocol that is very, very badly documented. The architecture is monolithic, so if you want to change something in the way the scheduler behaves, it's very hard. You have to compile your own version of Yarn, and if you want to change executors, then good luck, and so on. Mesos, on the other hand, was built to be extended. It has very good API, and it's very customizable, and you can change parts, executors and schedulers and so on. So if you plan on extending it, probably Mesos is a better choice. So the bottom line, why would you use Yarn and why would you use Mesos? The reason to use Yarn is you're probably already using it. If you have Hadoop, you have Yarn, there's really no reason for you to bother and put something else in place. Again, if you have Hadoop, then probably all of your applications support Yarn, and they don't support Mesos, probably. And it works pretty well. Despite its shortcomings, it works pretty well. There are also some benefits to having a monolithic scheduler. It has an easier time of allocating resources to a cluster. It's easier for it because it knows everything and controls everything. So if you have a very large cluster and you really care about utilization, then probably Yarn will do a little better job, somewhat. So if you want a data processing grid, then Yarn is probably the choice that you're going to make. On the other hand, if you have generic workload, if you plan on running web servers, application servers, machine learning applications, whatever, on the same cluster with data processing jobs, with batch jobs and everything else, then you probably want Mesos because it's built for generic applications, it's built for generic workload. It's very easy to extend, so you can always make your new application work on it. And it's a production workhorse. There is a lot more production experience when it comes to Mesos than there is with Yarn. Okay? A lot more people use Mesos in large scale in production than they do Yarn. There is a caveat here. Not in Israel. There aren't a lot of companies running Mesos in Israel, and there are a lot of companies running Yarn, not in large scale, but still a lot more companies use Yarn here in Israel than they are using Mesos. That's life. That's a bitch. So, it's probably a good choice if you're starting from scratch or if you want to run generic applications. So, next time we're going to talk about APIs, about containers, you know, how this stuff actually works in Linux anyway, how it behaves, like what happens if you run too much load in your cluster and needs to preempt your applications. We're hopefully going to do a demo if we have time, and we're going to discuss alternatives like Docker Swarm and Kubernetes. Okay? So this would be a good time for questions. Yeah?
What's the overhead of scheduling if you have many applications? And what's the overhead in time it takes to schedule in Yarn versus Mesos?
Okay. That's a very good question. What's the overhead of scheduling? So the overhead of scheduling varies greatly. It depends on the utilization of the cluster. If utilization is low, then scheduling is a lot faster. It also depends on the size of the cluster. It takes usually takes less time to schedule on a larger cluster because you have more options. Okay, small clusters usually take more time because with all of your nodes. So if you don't have enough combinations of slots available, then you have less options to schedule. There is a difference between the time it takes to schedule on Mesos and Yarn, and there are competing reports like the Mesos paper claims that the difference is not so big. It's I think they measured around 10% difference more or less, but it changes on depending on the type of workload, depending on the type of cluster, and that kind of stuff. And I can't tell you because I could never get the same cluster to run Mesos and then Yarn, because I'm not an academic. I don't have the time or the resources to take the same cluster, reinstall it with Mesos, and then do the same workload all over again with Mesos. So it's really hard for me to tell you.
What's the overhead
in time
of either framework compared to standalone?
Okay, so in standalone, the overhead is essentially zero because you don't do anything. Like you choose which node to run your workload on. You have all the resources dedicated. They're available when you want to run your job. So the overhead is essentially zero. With a grid of any type, you have non-zero overhead, and that can vary. It can be from less than a second if you have capacity available and it's basically copying the files and launching the process. It can be very, very fast. A little bit more with Yarn than Mesos because Yarn has to start your application master. Okay, but if the application master is already running, then again, the overhead can be less than a second, sometimes even less than, can be in the order of hundreds of milliseconds. If the cluster is busy and there aren't a lot of resources available, it can take a very long time. Okay, but that's the price you pay for utilization, prioritization.
In Mesos, the application master is always running?
The framework is always running, okay? And in Yarn, the application master is per job. So if you have like one very, very big job that keeps running or is actually running sub-applications, then you get very fast scheduling, okay? Please don't do that because this is not how Yarn is supposed to work. But yeah, people do that. Yeah.
You run the statistics in your business and you know that you always have your business always requires, this number of nodes to handle your day-to-day business needs, and you need the scheduler for when you have spikes in your spikes in demand and stuff. So is there a way to tell these frameworks to kind of set aside these nodes to always run these other nodes so you can bring down the scheduling overhead for those nodes?
Depending on whether you're talking about Mesos or Yarn. The question was, if you have a very spiky workload, where you only need a lot of capacity for some of the time, can you assign certain nodes on which tasks will not be preempted? Did I understand you correctly?
To basically use the frameworks to handle the spikes more, and then for your day-to-day workload to sort of set the
guaranteed resources.
Yeah.
Yeah. So Mesos does have a concept of guaranteed resources, which will never be preempted. And if your framework only uses guaranteed resources, then yes, your workload will be spared of preemption. It will not be preempted, and it will keep on running even during spikes. Again, it's a matter of quality of service. So a framework will not get all the guaranteed resources at once. There is a certain limit, but yeah, the concept exists. Yarn doesn't actually do a lot of preemption, so it's not really a problem in Yarn. Again, the price is utilization. Okay? Yeah.
I have two questions. First, can my process be actually a VM that is set up with all the stuff that it has to do? So my process will be just start this VM, and could I possibly correlate, let's say, the queue length on the RabbitMQ with the need to scale up?
So there are two questions here. One is, can you run a VM as a process on Yarn or Mesos? And the second question was, can you use the queue length of RabbitMQ or whatever queue you're using to auto-scale your worker nodes? The answer to both questions is yes, with a caveat. So can you run VMs on this kind of grid? Actually, both Yarn and Mesos have virtual machine support in the work plan. Okay, so I'm not sure exactly when they're going to have support for it, but it's planned. They're working on it. It's technically possible to run it even now. You can, for example, have a Docker container with KVM on it, and just throw it at Mesos. And assuming that you have kernel support, then it will probably work. It's a bit hacky, but it's going to work. If you wait long enough, you're going to have support for it both in Yarn and in Mesos eventually. The second question was, can you use the queue length to autoscale? And the answer is yes, but you would probably have to write some code for it. If you write your own application master in Yarn, then it's pretty easy. Just have your application master look at the queue length and start more containers when you need them. And if you're talking about Mesos, you would probably have to write a framework for it. Okay? Any more questions? It's going to be the last one because we're running out of time. Yeah?
Would you prefer running things like web servers, app servers on a platform as a service thing like Cloud Foundry, rather than Mesos?
It's not really related, but the question was, would I prefer using or running your applications on platform as a service rather than using grid? So Cloud Foundry, for example, and a lot of other platform as a service solutions that you find out there actually have a grid underlying them. For example, OpenShift from Red Hat uses Kubernetes, and Cloud Foundry uses something called Lattice, which is their own grid component. In general, platform as a service adds more services and more APIs on top of grids. Stuff like databases, service discovery, load balancing, queues, message buses, that kind of stuff. So if you want, yeah, sorry?
It consumes resources. It consumes resources.
Of course.
It
Of course.
competes with resource management.
Of course. If you're interested in those additional services, then probably yes. If you're not interested in those additional resources, then you're essentially running a grid, but with a lot of services you don't use. So that's the answer. So thank you very much.
only a small thing. We will have another continuum to this session, so please send us some questions. I have questions on my own, like things like grid metrics, pros and cons. I have a problem in Yarn, in Mesos, or things like that. We'll have another session in the 26th of August. So please send us some questions, send Avishai as well, and we'll try to answer what we can. Another thing, we'll have a break of 5 minutes, and we'll continue to Alex's lecture. And please answer a survey that I will send in the finish of the talks. Thank you.